our 15th lecture on power system operation and control. Here again, we are going to continue with our economic dispatch problem. So in the last class, we saw about a broad view of power systems. Am I audible and everybody can see my screen?
Yes, sir.
Okay, okay, good. Yeah. So, and then we saw some basic background of how these prices are decided by the generators, at what price they are going to sell their power. So this price is decided by the generators, and then this price we discussed in the last class that it is basically in this smooth curve, but ideally it is a smooth curve, but it is in a increasing sense, and you can call it as, generally we represent it as in a quadratic form. So you can easily say it is a quadratic curve, and practically obviously it is not smooth. There are few jerks in between. There are some non-uniformity also is there because of prohibited operating zone, and the Pmax and Pmin of a power plant or a generator is decided by their turbine limits and the boiler consideration. Right. So every time I am paying different price for generating additional generation, right? This is a bit confusing. From, let's say, if I take the price is just, let me make it from the logic of pen, or that let the cost of pen be ai into pi. The pen is the quantity and ai is the price of that, and c will be the total cost. Now if this is the total cost, then the price will be nothing but dc by dpi, which will be ai. Now if I have to plot this, so the total cost plot will be linear, and the price, so this is rupees, and here it will be, let's say, in terms of megawatt or per unit. And let's say if I have to plot the price, it will be rupees per unit, and it will be flat within the Pmax and Pmin range, right? Pmax and Pmin range. So is this clear to everyone that because the cost generally in let's say regular commodities, what we see, the costs are linear. So we know the price and number of quantity you buy, you just multiply that, and that will be the total cost you are paying. So the total cost is incremental, linearly increasing one, and the per unit price is always flat. So you are not changing the price by, let's say, if I want to buy a pen, and either I buy 10 pen or 100 pen, the price of the pen is going to be same. So that's why it is going to be flat, right? So this is the logic here. But if you will see from the generator's point of view, if you see that it is quadratic, that means what you can understand from this incremental cost curve is that the every extra generation of megawatt will actually increase the cost for the next generation, right? Or I can also explain you from the vegetable market point of view. That this is going to be very simple. So let's say if you want to buy, let's say, any vegetable, or let's say talk about fruits. So let's say if you want to buy an apple and you go to a vendor. Now what will happen is, let's say a vendor is having 100 kgs of apple. So obviously if the first person who goes to that vendor, let's say he decides a price for the apple is, let's say, rupees, I'm just giving 5 per kg, right? I'm just giving an example. So what will happen is, if let's say the demand, if more people are approaching for buying that apple, what he will do, that he knows that there is demand is more for that apple. He knows, and he has a limited supply of 100 kg. What he will do, that later on, probably after selling 10 or 20 kgs, he might increase the price to rupees 10 per kg. right? So just think from the vendor point of view or the seller point of view, that he knows that he has a limited supply, and because the demand is also increasing, so what he will do, he will increase the price so that he can earn more money for the next selling or the next kg what he is selling for apples, right? The same logic you can apply for the power system, is that because power, as you keep on increasing the generation from the generator, the next generation or the next megawatt of generation will require additional money for generating, or additional per unit price will be required for generating that extra megawatt. So I hope it is clear that this is actually a price which you can call it as lambda. We generally call it as lambda, which is nothing but rupees per megawatt. And I have mentioned that here, if you'll see, it is rupees per megawatt. Right. So I hope it is clear to everyone. I do not want to go more into it, but I hope the difference is clear. Okay, so let us see the mathematical modeling of ED problem. And we in the ED problem, we assume that the demand is constant. We assume that load forecast is already available and the demand is already available with us in megawatts. And as a ED problem, our objective is to identify the generation schedules such that the total cost is minimum and all the constraints, which are equality and inequality constraints, are satisfied. So from the economic dispatch point of view, the constraint, the objective function is just the cost function. So this FIPGI could be AI plus BI. So this could be like a quadratic function, summation I equal to 1 to ng number of generators, right? So you can write an objective function as this: minimization of ft plus summation I equal to 1 ng fi pgi. This is the cost function. So it is not necessary that every generator will have quadratic. It's a freedom of a generator, so he can either give a quadratic one, linear one, or a constant one. It is his choice, right? Now this is the objective function. Can you guess what is the constraints? What will be the constraints for this? What are the constraints for an economic dispatch problem?
Summation I equal to mg pgi should be equal to pd.
Yes, good, good. So basically, there is only one constraint, which is the one equality constraint, which is power balance, which you can say is basically sum of PG minus PD should be equal to 0, or sum of generation should be equal to demand. This is the only equality equation. Now, there is only one inequality equation, that all the generation should always remain within its lower and upper limit, right? So underscore means the lower limit, overline means the over limit of PGI, right? And this will be valid for all the generators, because obviously all the generators have some physical limitation, what maximum it can generate or minimum it can generate. Now, looking at this problem comes under a linear optimization problem, non-linear optimization. What type of optimization problem is it? Why?
Because objective function is not.
Yes, you can call it as non-linear. Okay, good. And what about convexity? Is it a convex or it is a non-convex? This optimization problem is convex or non-convex? So convex, I mentioned, if you search for a feasible space and then you pick any 2 points and you draw a line, that line should always remain within the feasible search space. So that means it's convex. If that line crosses, if you know this type of situation, then the line will always cross the feasible region, and that means this optimization problem is non-convex. So is it convex or non-convex? Let's assume there is only two generator. Can you now visualize it? This is actually a special case also. What you can say, it's a linear constraint quadratic programming problem, because objective is quadratic, constraints are linear, right? So this is a special case of non-linear. It's okay, means, but you can still guess on the convex and non-convex. Can you guess, is it going to be convex or non-convex? Okay, so let me make it make you visualize it. So let's say if there are two generators, let us talk about just two generators. So A1 plus A2 plus B1 PG1 plus B2 PG2 plus C1 PG1 square plus C2 PG2 square. Right, so this is going to be the objective function. Now can you visualize, is it going to be and because constraints are linear, so I'm not going into that, only the objective function is might be confusing you. So can you now visualize it, that it's going to be convex or non-convex? So let us, or even let me make it more simpler, because we know that PG1 and PG2 generation cannot be negative. So let's assume both PG1 PG2 minimum is 0 and both is 200. So both is 100. So let's say 100 and then 200. Right. Now let's say what you do, you create any combination of values of PG1 and PG2 between 0 to 100, because PG1 minimum limit is 0, maximum limit is 100, PG2 minimum limit is 100, PG maximum is minimum is 0, maximum is 100. So for both the generators, minimum is 0, maximum is 100. Now because it is a quadratic equation, can you see that this is a quadratic equation? So if it is a quadratic equation, the solution, whatever combination you will make, this is going to be like this. This is always going to be like this in this curve fashion, and there will be no jerk or nothing here. It will be always be smooth. If you try to find out the feasible search space, it will always be in this fashion, and wherever this sum of PG is equal to PD, so let's say if PD is 120, so here wherever it intersect this line, so let's say it is intersecting here, so that means here will be this will be a feasible optimal solution. So it's actually going to be convex because the feasible search space is always going to be convex. So if you visualize it, it is going to be like this, and then there will be a straight line corresponding to PG1 and PG2. So wherever it intersects this line, there will be the optimal solution. So it is going to be convex. It is going to be convex. So you have to actually
because of one global solution.
Yes, exactly. So now it is convex, although it is non-linear, but it is still convex, obviously, because it's a quadratic programming. And as soon as it is convex, you can guarantee that there will be a single optimal solution, and that single will be a global optimal solution. Right. So as soon as I mention convex, it is obvious that you will get a global optimal solution. right? So either any of the method you use, Newton's first order, Newton's second order, interior point, whatever we have discussed, even the KKT one, you will always get a global optimal solution and a same solution and also a global optimal solution, right? So now let us see how to solve it. Let us quickly see how to solve it. So let us for solving this problem, the first step is to write a Lagrange function, and after writing a Lagrange function, you can take the just observe that I have ignored the inequality limits. You can also add it because I'm not solving it based on the conventional method. I'm actually giving you a new method to solve it. So the actual method, you can anyway use Newton's first order method, Newton's second order, or optimal interior point method to solve these problems. And I'm not going into that because I'm assuming that you know all those methods, you have solved the tutorial, so I'm sure that you can solve the problem. I'll give you an example also so you can try it out on your own. But I'm just giving you here another method, which is like when we form a Lagrange function here, assuming that the inequality equation, which is just the generation limits, you can ignore that for a while. What you have to do is just form this Lagrange function in ignoring just the generation limits. Not if there are some other inequality constraints, you do not have to ignore that, only the generation limits. At optimum, what will happen is you will take the KKT in terms of all the variables, which is PGI and lambda, right? So PGI, when you will take, it will be dfi PGI minus lambda equal to 0 because PG is here, and then eventually you can say dfi PGI will be equal to lambda, and when you take the derivative in terms of lambda, it will be PD should be equal to sum of all the generators, right? Now from this equation, one observation what you can make here is that there is going to be only just one lambda. Why one lambda? Because there is only one equality equation. Now if there is only one lambda, but here if you'll see on the left hand side, it is dfi by dpgi, and I belongs to all the generators. So basically dfi dpgi is what? It is nothing but the incremental cost curve of generators. So basically what you can see here, that whatever is the incremental cost curve of the generators, this lambda will always intersect all the incremental cost curves. Sorry, I made a wrong curve. So let's say because incremental cost curve, right? So this is linear. I'm assuming that this is linear. And let's say one is starting from here, another generator is starting from here. So this is basically rupees per megawatt, rupees per megawatt, rupees per megawatt, right? For all the generators. And let's say G1, this is G2, this is G3. There can be many other generators. So this lambda, which is on the right hand side, this also is equal to dfi by dpgi, and you know that dfi pgi is nothing but rupees per megawatt, which is the incremental cost curve. So this lambda for all the generators has to be equal. From this you can imagine, so lambda will be nothing but a common line intersecting every value, and wherever they intersect, so this will be the generation by pg1, this will be generation by pg2, this will be generation by pg3, and this lambda eventually this we are going to see anyway in detail in the next course, which is power system deregulation. But I can tell you this lambda is a price which is being paid by the loads. So demand will pay, all the loads will pay at lambda to the system operator. Basically we pay our electricity bill to the state electricity board, and state electricity board eventually pay the bill to the system operator, and then system operator pays lambda to all the generators, right? So basically total payment will be lambda into PD, all the load will pay at lambda, which will be equal to total payment made to the generators, right? So this balance will always be there. Do you get this point? That whatever payment, so let's say if I buy 10 pens and the each pen has a cost of 10 rupees. So total I'm paying 100 rupees, and the company or the pen company will also get from at 10 rupees for the 10 pen 100 rupees. So there is nothing in between which is going out, right? Or maybe the company can distribute that 100 rupees with sellers and this dealers and everyone. That is going to be separate, but that is the generator has to take care. But here the balance will always be there, right? So this is clear, right? So lambda is basically the price which is going to be paid by all the loads, and lambda is the price at which the generators are going to get paid. Now the issue here is, let's say there is a fourth generator, and sorry, let me just make the third generator one of that sort, right? So let me make the third generator like this. Its Pmax is, Pmin is here, this is the Pmax. Now this generator is not touching this lambda curve because this Pmax has reached. Then how to handle it? Let us see that in the next slide. So basically, till all the generators are having within limit, are generating within the limit, then you do not have any problem. So you can easily calculate that. So let's say there are, let's say we are talking about 3 generators, right? So one will be B1 plus 2C1 Pg1 will be equal to lambda. B2 plus 2C2 Pg2 will be equal to lambda. B2 plus 2C, sorry, B3 C3 Pg3 should be equal to lambda. And then there is another equation that total demand should be equal to Pg1 plus Pg2 plus Pg3, right? And how many variables are here? Pg1, Pg2, Pg3, 3 variables, and lambda is the 4th variable. So you have 4 equation, 4 variable. You can easily solve this using a 4 equation 4 variable concept, and you can get the value of Pg1, Pg2, Pg3 and lambda, right? So I hope this is clear to all of you. And then my question was here to all of you is that if this type of situation happens where Pg3 is, you will obviously, because here we are not taking care of the inequality constraint, so Pg3 might be a value which is crossing its limits, or crossing its limits means either it is going beyond Pg max or it is below Pg min. So another case could be like this is starting from here to here, so this is Pg min and this is Pg max, so that could also be the case, right? Now how to resolve this issue of inequality in this type of setup? So I'm giving you another logic for ensuring that limits, and this will be clear once you solve the problem on your own. Yeah, okay, so that's what I am anyway mentioning here, that at optimality condition all the incremental cost of the generators must be same. So that's what I was mentioning here in this equation. So all the incremental cost of the generators must be same. Okay, so now handling the inequality constraint. So the method which I am telling you is nothing but the lambda iteration method. You can easily see in the books, there are many, or in all the books you will find this lambda iteration method. Any power system book you take as a reference, there you will get this method. So what happens, like if the generator is crossing its limits, or basically if it is Pg is greater than Pg max or Pg is less than Pg min, so basically it is crossing the limit, then what you will do, you will fix that generator at the limit. So let's say if this is the situation, so then what you will do is make Pg equal to Pg max, or if this is the situation, you make Pg equal to Pg min. So you enforce that equality, right? So as soon as you fix these variables, what happens is now this no more remains as a variable. It now converts to an constant value. It's a parameter now, because it is already known that this is going to be at this value, Now, once you know this value, what you will do, you will ignore this because you already know it. So what you will do, like PG3 was violating there, so you can make PD minus PG3 should be equal to PG1 plus PG2, right? Because and PD is also known, PG3 is also known, because either whatever it is limit is violating, you will fix that value and you will just have two variables in the optimization problem, and then you will solve that optimization. You will just take the KKT and you will solve that for two variables. You will see that there is going to be three equations and three variables, PG1, PG2 and lambda. So three equations, three variables, and you can easily solve it and you will get the values of PG1, PG2 and lambda. Right. I hope this is clear to everyone. If you have any doubt, you can stop me. Okay. So then what happens once you solve that problem, this PG1, PG2 equal to PD minus PG3. Now we have to check that PG3, which we assume to be fixed, should it remain fixed or should it change the value? So this will be decided by a logic which I'm going to tell you, and you will appreciate that logic, how we are going to do it. Basically, the idea is you have to compare the lambda values. And what do I mean by lambda values? Comparison of lambda values. You can easily visualize. I'll just give you a logic for one of the generator when that generator is hitting its max limit. How to see that generator is going to remain at that value, or you have to again create it as a variable, because right now PG3 is a constant. So we are cross-checking that PG3 has to remain constant or it can become a variable. So that's what we are going to cross-check here. So basically how we do that, just imagine that the lambda is going to be the price. That's what I mentioned in the last slide, that lambda is a price and that is paid to all the generators, right? Now, if let's say generator or PG3 was fixed at the maximum limit. So basically, if you know that generator PG3 is fixed at maximum limit, so dF by 3 by d PG3 is going to be B3 plus 2C3 PG3 max. So whatever is the max value, you can put it here. So this is the price what generator is actually incurring, right? Because this is the cost function what generator has given to the system operator. On the other hand, this lambda is a price at which system operator is going to pay this generator. Now what happens if let's say I call this price as alpha? So if alpha is greater than lambda, what does this mean here? Just try to visualize it, that alpha is the price what a generator wants when he is at PG3, and lambda is the price what system operator is paying to that generator. So for example, alpha is the price, basically you want 10 rupees per megawatt for your generation at PG max, but the system operator is paying you, let's say, 5 rupees per megawatt. So obviously you want 10 rupees, but the system operator is paying you 5 rupees. What you will do, a simple logic. Can you guess what the generator strategy should be? Can you guess that? Now?
Yeah.
What will be his strategy? He should not remain at its max limit, right? Because he can generate between PG min, PG max. So right now he was at this value, and he knows that at this value you can also calculate the alpha values range, right? So alpha value PG min could be, let's say, 2 rupees per megawatt, and here it is 10 rupees per megawatt. So what you will do, if that PG max is asking at PG max, as a generator I want alpha, which is 10 rupees per megawatt, but system operator is offering me 5 rupees. So what I'll do, I'll shift my strategy to remain at max, and I'll come somewhere in between. So basically I'll back off from the limit and then come to a value in between. So in between means I become as a variable. I will not remain as a constant, and then at the next iteration you again will have PD equal to PG1 plus PG2 plus PG3. So PG3 will again become a variable, because system operator is paying a less price what I want, so I will not remain at that value. I'll reduce my generation, so that because obviously the price should be equal to the value at what I am generating, right? Or more, or equal. I do not want it to be less, because if it is less, then my whole business strategy is gone, right? Because if I want 10 rupees and I'm being paid, let's say 5 rupees, so why will I run a business at a loss, right? So that does not make sense. So that's why I'll become variable, and then optimization problem will decide the new value for me. Now, the other way, obviously, you can think, if other way could be alpha is less than lambda. So that means the alpha is, let's say my asking price was 10 rupees per megawatt, and I was at my maximum limit at 100 or whatever is the megawatt, and system operator is offering me rupees 15 per megawatt. So what does this mean is that at my maximum limit I am asking for 10 rupees, but system operator is offering me 15 rupees. So it's a profitable business, right? Why will I reduce my generation and reduce my chances for earning profit? So what I'll do, I'll remain at my max limit, and then whatever system operator offers, if it is more than rupees 10 megawatt, rupees 10 per megawatt, I'm happy for that. So I'll remain at the limit. Right. Now, can you guess what will happen if the situation is reverse, and if the situation is basically I am hitting my lower limit? So let me just quickly ask you this question. Let me erase this. I hope you got the idea. So yeah, let me just quickly erase this. So this I can erase. So now the situation is that the generator is at its lower limit, right? And the price, so here instead of this it's PG3 min, and let's assume this is alpha. So what will happen if alpha is less than lambda? Basically my asking price when I am at minimum is, let's say, rupees 2 per megawatt, and system operator is offering me, let's say, rupees 5 per megawatt. So what should be my strategy? Should I remain at PG3 or should I become as a variable? And the another question is going to be, what will happen in this case when alpha is less than lambda? What will happen to PG3? Will it remain at its lower limit?
So it will remain at its lower.
In this case,
So when alpha is less than lambda.
so again, just think. Okay, I anyway wrote here, but anyway, so just think from this point that alpha is the price which I'm asking as a generator. So I want 2 rupees per megawatt, and I am happy with that. Now system operator is offering me 5 rupees per unit. So what will happen? Why will, so PG min, PG max, right? Now, okay, I'm not disclosing the answer. Think from this point. Now, alpha is greater than lambda. Was it Nivedita, right? You answered it. So,
No, sir.
or Adyasha? No.
Sir.
Okay.
No, sir, because the price offered is more, so I should increase my generation to get more profit.
Yes, exactly. So basically, if the price offered to me is more and I have a margin to generate more, then what I'll do, I'll not remain at my limit. I'll say, okay, now increase my generation because I have more option to earn more money. So what I'll do, I'll generate more and I'll earn more profit. So I can generate more. So in this case, again, PG will not remain at its lower limit PG3 and it will go become as a variable. So this is again the same situation of this. Now think from this that alpha is greater than lambda. So now my asking price is 2 rupees, but the system operator is giving me just 1 rupees per megawatt. So what I'll do, because I am already at my minimum limit, I cannot reduce any further to match this price. So what will happen that I'll always remain at my lower limit, and whatever generator is offering, I'll take that price, right? So this is what we are going to see here. You can visualize it. This is going to be very interesting, that if my asking price is more than what is being offered, so basically here alpha is greater than lambda, so then I remain at limits what I raised from here, and when alpha is less than lambda, then I can generate more and increase my options to earn profit, right? So I will move. So basically this is the strategy what you will do in lambda iteration method. In every iteration you will keep on updating your status based on this method, and wherever you get converged, you will settle down there. I'll give you an example for this and you can solve it and you can cross check all these strategies what I'm telling you, and then you will get a better feel of it. Just let me take few more slides. And obviously this lambda iteration method, you can easily visualize this logic is good for small set of generators. If the set of generators are huge, it is very difficult to handle this inequality constraints very well. So obviously you can use any Newton based methods and get the solution in a much faster way. Okay, I hope it is clear to everyone. Now let us see an example. Here we have three generators. One is coal-fired steam unit, one is oil-fired steam unit, another is also oil-fired steam unit. I have given you the max min input and max bit output of all three generators. Input output curve characteristics I have also given you, and I'm also giving you the fuel cost. So it is 1.1 rupees per MBTU and 1 rupees per MBTU, 1 rupees MBTU. So to calculate the cost of it, so let's say if I want to calculate the cost function of this first generator, then it will be H1. You can just see the dimension H1 into the fuel cost. This will give you the dimension as MBTU plus per hour into rupees per MBTU. So then this will go away, then this will give you rupees per hour, right? So this will give you the price, the cost of this plant. So you can similarly calculate the cost of all the plants, and the demand what I'm giving you is 850 megawatt. So basically there are three generators, PG1, PG2, PG3. The demand is 850 megawatt. You have to calculate, the lower limit, upper limit of all the generators. You have to run that lambda iteration method and calculate the optimal generation. And so you need to calculate the values of PG1, PG2, PG3 and lambda at each iteration, and eventually you have to tell me the converged solution. So I know because it is going to take just 2 iterations, so you can easily solve it and tell me the answer in the next class. Okay, so this is going to be your quick homework type of thing, You can solve it and tell me the answer in the next class. Okay, now also if I change the fuel cost of unit 1, rest all unit remains the same. I just change the fuel cost of just the unit 1 from 1.1 to 0.9 rupees per MBTU, and then what will happen to same PG1, PG2, PG3 and lambda at the end of the iteration. So final iteration of the lambda iteration method. So you have to tell me the value for these two examples. So though there are two examples, both examples will obviously have different solutions. Let me know in the next class, are you able to solve it or not? Okay, otherwise we'll see, we can solve it for you on tutorial, but you can tell us the answer in the next class on Monday. Okay, I hope it is clear to you. Now the last one is basically we saw just this. I'll complete it quickly and then I can close this today's session. Is basically we are solving economic dispatch without losses. We are assuming that there is just a single bus and all the generators are connected here and a load is connected here. Then we are giving you the optimal solution. But practically, obviously there are transmission lines, and if there are transmission lines, and then every line has its own resistance, and obviously current is flowing on each line. So obviously because of I square R, there will be some losses of power. And earlier before 1950s, this was not an issue, much of an issue. But what happened after 1950s, specifically when the network size started increasing, we have started facing that issue that the losses are increasing at a very high value, and we have to incorporate the effect of losses in economic dispatch. And this incorporation leads to some modification in the conventional economic dispatch model what we saw just now. So that model modification we'll see in the slide, and then probably how to solve it in just 2-3 slides more. But I'm not going to cover all these. I'll just cover this slide in today's lecture, and then the solving method I'll tell you in the next lecture. So basically what we do here is obviously there was no method to model the network. So in earlier days, people used to add a representative loss as a loss formula, and what people did, that the loss formula what they derived is P loss equal to Pi, Pj, Bij, and Bij is nothing but a matrix for which will be number of generators cross number of generators. And what will happen is it will have some coefficient values which will tell you the correlation. If the power is coming from a particular generator, how much loss that will lead to. So this is the way this formula was derived. I can tell you the derivation if needed, but this is not that necessary. But this is the basic elementary formula what people have derived, and based on this B factor, they keep on, as they are installing more lines, more generators, they keep on updating this Bij matrix, but they derived this formula, and based on this they used to allocate the losses across the network. There are various other formulas where you can also find constant and linear terms. I'm not going into that. That is not that important. If you understand this, the others also you can easily understand. So these Bij matrix, this equivalent loss coefficient matrix, basically they calculate these coefficients based on some representative load conditions, which is basically peak load, medium load or low load. They will just calculate it and keep it readily available with them. And whenever, depending on this network or demand situation, whatever is the load, if load is very high, they take the Bij matrix, which is corresponding to the peak load. If the load is very low, they take the Bij matrix corresponding to the low load condition. So they derive this loss coefficient matrix from basic load flow representative method, and they get this matrix formation, and they keep it ready. Whenever they need it, they can easily use that particular Bij matrix, and they can represent the effect of losses in the economic dispatch. So this is the way they used to do in early 50s, and after 1960s the thing has further changed, so that we are going to discuss probably after 1 or 2 lectures. But how things have changed we are going to see gradually. So I'm starting from a very old point of view, earlier days, what people used to do, and just make a note of it that this economic dispatch is still very important, although I'm teaching something which is 70 years old. But this is still very important because today still people use economic dispatch across all the power exchange of all the countries. So it is, we cannot say that being 70-year-old it is still not of use. So it is still in use. That's why we are teaching it, right? So I'll